Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we're going to learn about memoization. We hear about memoization very frequently with coding interviews, especially when we're discussing dynamic programming. But in addition to coding interviews, it's something that we use very often in real life. We use memoization all the time in our code. And what memoization is an optimization. It's a way for us to speed up the code that we use. And the way we speed up the code is anytime we have an expensive function call or any expensive calculation, we store the result of that calculation so we don't perform it again. So we only perform the calculation once and then use the stored value each time afterwards to get fast access to that data that we need. So for example, if we call a function with the value 10, anytime we execute that function again with the value 10, we just return the stored value. And typically, we get this speed improvement by incurring additional space. So very often we add an additional data structure like a hash table that will allow us to store and access data very quickly. And in interviews, we most frequently see memoization with dynamic programming, where we memoize the results of overlapping subproblems to speed up our solution. So memoization is a form of caching. We store data and we want fast access on it later. And we typically introduce a data structure and most often a hash table to store this data. The key in the hash table is the function input. And then the value stored in the hash table for this key is the return value from the function. So then if we call the function again for this function input, we just access the result from the hash table and return that. By doing this, we can return immediately and remove the need to execute all those operations within the function again. So now let's see an example in code of how memoization works. We're going to write a function count by 2 and have a non-memoized version and a memoized version and see the difference. And it's worth noting that this example is a bit contrived. Obviously, we don't need a loop to count by 2, we could just double something. And for coding interviews, we don't actually use a memoization on multiple function calls, we actually just use the memoization within the function solution. So what we do is we have sub-problems and sub-functions, where we store the values in a memoization hash table and build up the solution within that function. So let's first look at the non-memoized version. We take a value 10, we start at 0, and we go from 0 to 10 and add 2 each time. So 0, 2, 4, 6, 8, and so on, until we reach the value of n, which is the number of times we wanted to add 2, or count by 2. Then we return that count. And we can see this operates in O of n linear time, because we go from 0 to n each time. For the memoized version, we first initialize a hash table. Then within the function, we check if we've calculated a solution for this value of n before executing the function. So if this value exists, we simply return it as the solution for this value of n. If it doesn't exist, then we need to calculate it. Again, we start at 0 and go from 0 to n. Each time we add 2, but then we store the result for each value. So from I to n, these are all different possible values of n that this function could be called with. So at I equals 0, the count equals 2. At I equals 1, the count equals 4, and so on until we finish the loop. Then we've calculated the nth value, so we return the memoized version for the solution input. But then, on any subsequent call, if we've already calculated a value of n for the solution input, we can return immediately, and this operates in constant time. Instead of performing an O of n linear time loop each time we want to calculate the value for n, we can return immediately in constant time every time we've seen it after we calculate it for the first time. This is the power of memoization. Getting fast access after you've performed a calculation, and removing the need to perform these calculations again. And now, let's take a brute force version of the Fibonacci function and see how we can use memoization to optimize it. So to calculate the nth Fibonacci number, it's just the Fibonacci number from 1 behind it, and then the Fibonacci number from 2 behind it. And we can calculate this recursively until we reach the base case and we just return n. And here on the right, we're calculating the 7th Fibonacci number, so fib of 7. When we call fib of 7, we then need fib of 6 and fib of 5 to find it. For 6, we need fib 5 and fib 4. For 5, we need fib 4, fib 3, and so on until we reach the base cases. So when we try to find the Fibonacci function recursively, after we call the first function, we spawn many additional Fibonacci function calls. But in addition to that, we actually call the same Fibonacci function, or find the same Fibonacci number, multiple times. For example, to find Fibonacci of 4, we need 3. We find Fibonacci of 3 here, and here, and here. We see we also calculate 4 multiple times, so we have a lot of this repeated work. We have these overlapping subproblems. But what we can do is use memoization to store the results from these function calls so we don't call it multiple times. For example, after we calculate Fibonacci of the 4 for the first time, we store this value and then just return that value at each additional function call. And we do this for all the Fibonacci numbers after we calculate them for the first time. And the way we're going to do this is by using a hash table. So we create the hash table. The key is the nth Fibonacci number. And the value in the hash table for that key is the return value from the function for that Fibonacci number. So Fibonacci of the 0 is 0. Fibonacci of the 1 is 1. 2 is 1. 3 is 2. 4 is 3, and so on. So the key in the hash table is the Fibonacci number. The value for that Fibonacci number is the value for that key in the hash table. And then anytime we want that value, we don't need to calculate that nth Fibonacci number again. We can just return immediately in constant time. So now we have the memoized version of Fibonacci. We initialize a hash table. Then when we recursively call it, if we've already calculated this Fibonacci number, we just return it from the hash table in constant time. So we remove the duplicate work and no longer need to perform these additional operations. We stop from spawning these additional recursive function calls and can just return immediately after we've calculated it the first time. If we haven't calculated the nth Fibonacci number yet and stored it in the memoization hash table, then we need to do this the very first time. So we calculate the nth fib by calling n-1 and n-2 in the Fibonacci function, and then we store it in the hash table. Then after it's stored, we simply return it to the function that called it for the first time. So let's see how this improves the solution. All the white values are the first time we're calculating the nth Fibonacci number, or the first time we calculate the 2, 3, 4, 5, 6, and 7th Fibonacci numbers. Then the blue values are the ones that we've memoized. So after we calculate it for the first time, we store it, and then can just return this value immediately. So when we do that, not only do we return immediately, but all these additional recursive function calls never run. We just return the value that we had stored each time that we see that we're trying to calculate it. So we remove all those operations that were within this box. A brute force Fibonacci function operates in O to the 2 raised to the n power. But now, using memoization, it operates in O of n linear time because we remove these additional function recursive calls. And we do this by using a hash table and accessing it in constant time for all the subsequent calls. Now let's perform a practical comparison of a brute force Fibonacci solution with a memoized Fibonacci solution. We're going to calculate the same Fibonacci number. In each solution, we're going to calculate the number of operations or number of recursive function calls that it takes to calculate the nth Fibonacci number. The brute force solution is one that we've seen many times. The nth Fibonacci number is just the Fibonacci number of n-1 and n-2. For the memoized version, we initialize the hash table, which we call memo. Then we have the same recursive calls and the same base case, but we also check if we have the memoized version in the hash table yet. If we do, we don't execute the function. We simply return this value as the solution. If we don't have this value, we calculate the Fibonacci number of the n-1 and n-2, and then we store this value in the memoization hash table, so then if we encounter it again in the recursive calls for those overlapping subproblems, we're able to return it here. So after we calculate the nth Fibonacci number, or fib of the n, for the function input, we store that solution, memo of the n, for that value. So we execute these functions for the same Fibonacci number, and then we print the number of operations it took for each to compare them. So first we'll find the 25th Fibonacci number, or n equals 25. We can see at 25, there's a huge difference already. For the memoized version, there's only 49 function calls, so n times 2 approximately, but if you drop constants, that's just O of n linear time. However, the normal Fibonacci, or brute force version, had over 240,000 operations. We can see that without memoization, it requires many more operations to find the Fibonacci number because of that branching and overlapping subproblems that we solved multiple times. We continue to trigger these recursive calls deeper and deeper into the recursive tree, so we get a lot of branching. This is why we have so many of those operations. Now let's drop down to 10. We run it, and we see that there wasn't as dramatic of a difference, 19 versus 177. So this lets us see how bad it scales. Going from an n of 10 to 25, went from 177 to over 200,000 for the brute force Fibonacci solution. And we know the brute force Fibonacci solution has a time complexity of 2 raised to the n, so it scales very bad. Now let's increase it over 25. We go to 40, and there's a noticeable amount of time it took for my computer to solve it. And going from 25 to 40 greatly increased the number of operations to calculate the nth Fibonacci number. However, when we memoized it, it's only 79, so still linear time. And this is the power of memoization. Because we store these values, we don't need to recalculate them. We can just use those stored values where we incurred space complexity to store them to get this optimized time complexity. So we've seen that memoization works for top-down Fibonacci, but it also works for bottom-up. When we're calculating the Fibonacci number, we can store the numbers behind it and then just access the hash table and use those previously calculated values to calculate the current Fibonacci number until we reach the one that we're looking for. And we know for Fibonacci, we don't technically need the hash table, we only need 2 variables, but it's helpful here to see how memoization can be used for bottom-up as well as top-down, because when we get into dynamic programming, we actually use a hash table like this very often to create a bottom-up solution. And finally, let's look at some real examples of memoization to see how it's used in a practical context. On the front end, we maintain complex state. We fetch items from APIs and calculate the values shown on the DOM. Since we manage a lot of data, we typically store this data in state on the client and only update the small pieces that change instead of recalculating everything anytime we have new data. On the back end, we often have complex business logic, and we want to store those expensive calculations so we don't have to recalculate them frequently and can just use those stored values. And finally, databases can be very slow to query. When we do have slow queries, we usually want to store these in a memory database like Redis so we can cache the results and access them very fast on subsequent reads. Thanks everyone, and I'll see you in the next lesson.